it could be the roller coaster. It could be the stopper on the end of a string being whirled, turned around in a vertical circle. It could be a car going over a hill. There's one question you probably said where the car is going through a valley and then goes over the hill. So all those differ. We're really only interested in grade 12. We're only interested in the lowest point and the highest point of the circle. Because once you get to the sides, things are beyond what we deal with. So you're only looking at the bottom and the top. So if you can draw a free body diagram for a car at the bottom of the valley and the car at the top of the hill, you're good to go. Or if you can draw the free body diagram for the roller coaster at the bottom versus at the top of the loop, then you're good to go. So let's start with the case of the whirling stopper. So the stopper's at the top, stopper's at the bottom. So when the stopper is at the top, we've got a downwards force of tension. We've also got the downwards weight of the stopper. And that's causing the downward centrifugal acceleration towards the center. When the stopper's at the bottom, we've still got the upwards force of tension, but now we've got a downwards weight vector, but our acceleration still needs to be towards the center. And if it's uniform circular motion, the acceleration needs to be the same in both cases. So we should really be calling this FT1 and FT2 because they're going to differ. And what's the relationship going to be? Which one's going to be greater, FT1 or FT2? How does FT1 compare to FT2?
FT2 is bigger.
FT2 is going to be bigger, that's right. If this string is going to snap, it's going to snap when it's at its lowest point. And if you've ever been whirling something around, that's when it will tend to snap at its lowest point. Because that's when there's this opposing weight vector, which is tugging even more, right? Okay, so I assume that given a free body diagram, then you can go ahead and just go through that same process of applying the second law, centrifugal acceleration, v squared over r, substitute your 2 pi r over t if you need to, and so on. So this would be the whirling stopper. Now let's look at the roller coaster. So for the roller coaster, we'll just use a marble instead. If the marble's at the bottom, we've got downwards weight vector, upwards normal force vector, and which one is greater? Normal force or weight?
Normal force.
It has to be, right, because there's this acceleration upwards to the center of the circle. And at the top now, there's the downwards weight, but now the track is above pushing down the marble. The marble's going fast enough to maintain its wheels, or to maintain itself on the track. We've got a downwards normal force. So it's the sum of these forces which acts as our centrifugal acceleration vector, our centrifugal force vector. And it's the same, except now it's not tension, now it's normal force keeping the object in the vertical circle. Now in some questions it will say, what is the minimum speed? For example, what's the minimum speed that the marble needs to stay in the loop at the top? So the minimum speed is the speed at which, at the very top of the loop, the marble leaves the track by one atom space, and then immediately returns to the track. Any slower, and it's going to come up like this. Okay? So if your marble's going too slow, it might not even make it up, right? So it might just go up and come back down. If it's going fast enough, it'll make it up, then it will come back down. And if you actually get it over here and it's not fast enough, it's going to come like that and then bounce. So at some point, you're just fast enough to make it over, and then it comes around at some point. So you're looking for that speed. And at that time, it just barely leaves the track at the top. Likewise with the rubber stopper going around, right? Your force of tension goes to 0 for the instant it's at the top. Any slower, and it's the whole rope is just going to sag and you're going to fall. All right, and then the other case was you got a car which drives through the valley and then drives car which goes, say, over the hill and then through the valley. So again, we'll use a marble instead of a car here. So when the car is at the top, or the marble's at the top, we've got normal force, we've got normal force and the centripetal acceleration towards the center, so our weight vector is greater. And we're at the bottom, we've got normal force and the weight vector, centripetal acceleration towards the center. So the maximum speed that the car can go over the top with is the speed where it just leaves the track. So it catches air by like one atom's width at the very top, and then returns to the track. And that's how you would solve the problem in your book there. So let's see, are there any other cases? That's pretty much the three cases that you guys had to deal with. In our next model, we'll be dealing specifically with gravity as a centripetal force. So we'll be getting into universal gravitation, planets, and that sort of stuff.